Hey everyone! In this video, we're going to be taking a look at parallelograms in the coordinate plane. And more importantly, we're going to be taking a look at how can we justify that a quadrilateral is a parallelogram using our different tools we have in the coordinate plane. So to begin with, it is important to remember that when we're in the coordinate plane, we're able to use a lot of our tools from algebra. So we can use things like the midpoint formula, the distance formula, or the slope formula to help us out. So on the screen, I have the 5 different things that allow us to justify that something is a parallelogram. We have the definition, which says show that both pairs of opposite sides are parallel. Well, in the coordinate plane, I know that I can show that segments are parallel to each other if they have the same slope. And because I know the slope formula, that one seems pretty straightforward. Parallelogram opposite sides converse, if we show that both pairs of opposite sides are congruent, in other words, that they have the same length, that means it's also a parallelogram. In that case, we can use something like the distance formula or the Pythagorean theorem to show the lengths of each side. And as long as we have the opposite sides matching up, we know that it is a parallelogram. Parallelogram opposite angles converse, this one also shows that it's a parallelogram, but it can be a little difficult to find angle measures in the coordinate plane. Opposite sides parallel and congruent. So this is sort of a combination of the first two. So we have parallel side and it has to be congruent. So we can use a combination of the slope formula and the distance formula. And then the last one, the parallelogram diagonals converse, which shows that the diagonals bisect each other, and then it would give us that we have a parallelogram. If the diagonals bisect each other, it means that they cut each other in half, which also means that they share a midpoint. So if I take a look at the diagonals and I find the midpoint of each one, if that midpoint matches up, well, then we have a parallelogram. So what I'd like to do is take a look at 2 examples. I'll talk through which one I think would be easiest to use in each case, and then we'll justify that it is a parallelogram. So the first example, quadrilateral ABCD has the vertices 0, 0, -2, -2, 2, -4, and 4, -2. And I want to show that this is a parallelogram. So let's start by graphing this. So we have A is at the origin 0, 0. B is at -2, -2. C is at 2, -4, 1, 2, 3, 4. And then the last point, D, is at 4, -2. So 1, 2, 3, 4, and -2. So this was A, B, C, and D, and I will connect these together to create our quadrilateral. Now, one thing with this quadrilateral, we don't have any horizontal or vertical segments. If we did, that makes finding the length of those segments very simple because we can just count it or we can just find the difference in the x or the y values. Well, in this case, none of these are horizontal or vertical. So if we wanted to find the length of the segments, we would have to use something like the distance formula. But for this first example, why don't we just show that this is a parallelogram just by using the definition? So the definition, we need both pairs of opposite sides to be parallel. Well, we can do that with the slope. So let's find the slope of each of the segments. So let's start with AB. So now I can use the slope formula, which we subtract the y values in the numerator and we subtract the x values in the denominator. So for AB, we have -2 minus 0, and in the denominator we also have -2 minus 0. So that's going to be -2 over 2 with -2, which is equal to 1. Now let's do for BC. So going along at the bottom here. So our slope, if I subtract the y values, that's going to be -4 minus a -2, so that's going to turn into +2. And then we have 2 minus a -2, so again, that's going to be +2. So we end up with -2 over 4, which simplifies to a -1/2. I always want to simplify my slopes because it is going to make it easier to compare them, which is what we want to do. All right, so now CD, So CD, the slope here, subtracting the y values, we have -2 minus a -4. And for the x values, 4 minus 2. So this is going to be 2 over 2, which simplifies to 1. And then our last segment, AD, which I can use the slope formula again, or because I already went through the work of graphing this, we can actually count out rise over run. So if we take a look going from A to D, looks like we go down 2 units, and then we run, so we're going to the right 4 units. So that means the slope, my rise was -2, I went down 2. My run, I went to the right 4 units, which simplifies to -1/2. So now taking a look here, AB has a slope of 1, CD has a slope of 1. Because they have the same slope, that means that AB is parallel to CD. BC has a slope of -1/2. AD has a slope of -1/2, so that means that those two segments are parallel. So that means we also have and BC is parallel to AD. And if those two things are true, that means that this is a parallelogram because of the definition of a parallelogram. Now, let's try one more example, and we'll justify that one in a different method. So we have quadrilateral JKLM with the vertices -3, 5, -4, 1, 2, 3, and 3, -3. So let me just graph this, and we'll take a look. All right, so I graphed the quadrilateral, and now let's justify that this is a parallelogram. So again, this one doesn't have any horizontal or vertical segments. So the distances, we would have to go through the process of using the distance formula or the Pythagorean theorem. But I think in this case, let's use the parallelogram diagonals converse. So that involves the diagonals having to bisect each other. As I explained, if the diagonals bisect each other, they cut each other in half, which means that they have to have the same midpoint. So if I draw in these two diagonals, what we want to show is that this intersection is the midpoint of both of these diagonals. So let's take a look at the diagonal KM, and let's find the midpoint for this. So the midpoint, remember, it's the average of the x values and the average of the y values. So we add the two x values together, divide by 2, and we add the two y values together and divide by 2. So for Km, we have -4 plus 3 over 2. And then the y values, we have 1 minus 3 over 2. And then simplifying this, -4 plus 3, that's going to be 1/2. And then for my y values, 1 minus 3 is -2. -2 divided by 2, we get -1. And now hopefully, if we find the midpoint of the other diagonal, JL, we should end up with the same thing. So the midpoint, so our two x values for JL, we have -3 plus 2 over 2. And then for the y values, we have -5 plus 3 over 2. And then simplifying this, -3 plus 2 is -1. Over 2 is going to be -1/2. And then -5 plus 3 is -2. Divided by 2 is -1. So the midpoints are equal to each other, which means the diagonals bisect each other, which means that this is a parallelogram. And just to summarize these findings, so KM, which is one of our diagonals, and JL, which is the other, bisect each other. And because they bisect each other, using the parallelogram diagonals converse, we know that JKLM is a parallelogram. So we can use any of those 5 theorems or definitions to help us show that a quadrilateral is a parallelogram. But when working in the coordinate plane, we need to remember the tools we have at our disposal Using algebra, we have things like the midpoint formula, the distance formula, or even the slope formula. Once we're able to show a few pieces, we can use one of those theorems to justify that yes, it is a parallelogram.